Good afternoon, everyone. Okay, today is the lecture number 4 of this heat treatment class, and so this first topic is we will discuss some questions first. These questions are based on the previous lecture, and soon we'll move to the topic. So first question is why steel must not be taken to very high austenatizing temperature during heating cycle of the heat treatment, like 50 degree above upper critical temperature. Upper critical temperature for hypoic tektonic steel is A3. So can you people answer it? Am I audible to everyone?
Yes, sir.
So can you people answer this one? Why we must not?
Sir, grain coarsening will occur.
Grain coarsening will occur. Okay, fine. Why the grain coarsening will occur? What is the reason?
More diffusion at high temperature.
Yes, high diffusion, high temperature, high diffusion rate. Pressure, high diffusion rate. Okay, fine. So what will happen if the diffusion rate will be high? Grain will become coarsened. Then what will happen finally?
Strength will decrease.
Yes, coarser austenite grain. So if coarser austenite grain will be there, what will happen finally?
We'll get our product grain coarser.
Yes, very good. Product grains are coarser. Right, very good. So finally, what will happen to the result will be poor mechanical property or poor strength, poor toughness. So that is the main issue, right? Okay, very good. So next, decarburation also occurs. Decarburization means removal of carbon from the surface of the steel, right? So basically, this is called removal of carbon from steel surface. So can you tell me what will happen if the carbon will be removed from the surface of the steel? What is the consequence of that? What is the effect of carbon on steel or on iron? When you add carbon into this iron, what will happen? What is the property you are?
Sir, it becomes more brittle.
Yes.
Sir.
Last critical.
The expansion
Low volume.
is at high temperature.
High volume thermal.
You are saying low volume hood, low volume. Is the duration of- there is a thermal expansion of material. Tell me why is the cause of this thing. What is consequent? What is the reason behind the quench?
It's a thermal shock.
Shock. How? Can you justify that?
रैपिड कुलिंग होची ना तो डायरेक्ट माने बहुत कम टाइम रे जो टाइम टा दरकार एक्स माने कंट्रैक्शन हवा पई एटा ही कमी जाउची
Fine, but read it here.
Surface wants to control the inner
Is that gradient. Action is there. In time. Understood now? To opposite when will get cooling to mission both opposite here will get अभिभूषण के लिए अभिभूषण So these are the problems. Next, we'll move to another question: why holding time is most
for complete transformation in core part.
very good. Or it is required for will body short. I can write yes. Homogeneous temperature. Homogeneous. Homogeneous structure means I'm talking about homogeneous temperature because will not be. Everywhere from the some time. Question is
Different.
for how different?
Alloy needs more time.
Alloy needs more time. Why alloy?
So that carbides to be soluble in austenate, they need more time.
Very good, very good. So see, our priority is but all the initial structure, initial single phase, that is austenite. If we have a precipitate like carbides, right, typically formed due to alloying elements. Alloying element react with carbon to form carbides. They are strong carbides dissolved into the austenite. That's why it dissolved into the austenite more time. Because do not easily diffuse. The diffusion rate is very, very slow for heavium. Rate of diffusion is very slow. Sluggish. Term it is called sluggish. That's why sometimes we need high temperature also. Alloy steels needs more holding time. Make a holding time. Why? Because rate of diffusion is low. Times resolution it more time. More time in austenite phase. Best example is niobium. So these are the questions and answers. And why cooling rate is most answer? Cooling rate is most important cycle in the heat treatment. I can write.
The property of the product depends on the cooling rate directly.
Yes, cooling rate decides kind of what kind of product? Kind of product. Products means microstructure. Forms. Austenite. What are the product? You remember perlite or martensite? This is one. And any other point? In size. Size. Depends upon rate. Okay now? Cooling rate is fast. If cooling rate is slow, grain size is bigger. That is another part. Size also depends on cooling. These are the answers. Another thing is sectional area that are different. Now we'll move to cooling curve. Okay, fine. Now we'll move to cooling curve for a pure iron. Curve of a copper, and this is the curve of a pure iron. Can anybody remember what is the definition of a cooling? How cooling curves look?
It's a graph between time and temperature.
Very good. It is a plot between temperature versus time. not
Yes.
time and temperature. Temperature was time, temperature in the y-axis and time in the x-axis. Temperature versus time. What is the starting material we take in the cooling curve always? What is the starting material?
Liquid iron.
Liquid, yes. Here it is liquid iron and liquid copper. So you have to take a liquid metal or liquid alloy. Then what is the next stage is what you have to do? Cool it very slowly. But here, what we do, just listen it carefully. Huh? This is the cooling curve of a pure iron and this is the cooling curve of a pure copper. So cooling curve of a pure iron means temperature versus time for pure iron. Temperature versus time for copper, right? So we have to take a molten iron, pure molten iron at a very high temperature, and we'll cool it to the room temperature. And the cooling should be very slow, right? And what exactly we do? We also measure the temperature, how the temperature is getting reduced slowly with time. This is the time axis. So with time axis, how the temperature is getting reduced. We have to see that here also. So can anybody figure it out? What is happening here and what is happening here? What is the difference here? Difference between the cooling curve of a pure copper and pure iron. Just tell me.
Iron has different allotropes.
Iron has different allotropes, but that is not the answer. Just tell me what is the answer here? What you are
Different
getting here?
structures.
Different structure or different? What are these?
A crystal structure.
Stru-
No. You are not. Don't go to the direct answer. Tell me just what you are looking at. What is here and what is here?
Different steps.
Different steps. Very good. That is we can able to see here, right? In case of iron, we can able to see different steps, like your staircase, right? You can step over here. You can step over here. You can step over here. Like you can go rise. But if you are want to from top to bottom, you can go here. You can go here like this. So you can able to see different steps. But what about copper? We have a single step. Here multiple steps. What is the observation you can write? You should also write it down, huh? In this observation, we can see in the cooling curve of a pure iron, we have many steps. But here we have a single step. So now why we have a single step? Now why we have multiple steps? Can anyone tell me?
Copper is single phase.
Copper is single phase. So that means starting from the molten state to the room temperature, copper is, that means entire solid phase is FCC, right?
Yes, sir.
Yes,
Starting
sir.
from the, yes, that means from here, just look at this point. Do anybody remember what is, okay, let me expand this. Okay, what is this point and what is this point? Anybody remember? What is this point?
Solidification starting point.
Solidification
And solidification end point. Very good. But it is a horizontal line. That means solidification is happening at a constant temperature, right? It is okay. Solidification is occurring at a constant or freezing point. You can say this is a melting point or freezing point. Solidification is occurring at a constant temperature. But that means from here to here, what is the phase? Solid phase. So entire solid phase is not showing any kind of steps. Entire solid phase is not showing any kind of steps. That means it has a same crystal structure in the solid phase, FCC. But what is happening here? Okay, sorry. What is happening here? You can see it is molten liquid iron. But when you are cooling the sample slowly, but here what is happening? This is freezing is happening here. Solidification will start here and end here. So you get a step. But what about, that means this point is solid iron and this point is also solid iron. Entire is a solid iron. But entire solid iron is showing some steps. So why this is so? Due to what? This written over, it is written over here already. You can see.
Change in crystal structure.
Change in crystal structure. Very good. So that means copper is not showing any kind of change in crystal structure with change in the temperature. Whereas iron is showing some change in crystal structure. The BCC iron is changing into FCC. Then again FCC iron is changing into BCC. Here. This part. Right? This area is BCC again. From here to here it is BCC. From this point to this point, it is BCC, but here to here, it is FCC. From here to here, it is BCC. So that is the reason we are getting some steps. But what is the why we are getting steps? That is the question. So you can see. Let me explain it from here. So here it is molten liquid. So molten liquid iron is getting. It is the temperature is going down. The temperature is going down with time. But a point comes here when the temperature is getting arrested. Listen it carefully. There is a temperature arrest. So what is the observation? You can say we can able to see some temperature arrest in this cooling curve. So this is the temperature. Temperature arrest means temperature is not getting changed at that particular temperature. Temperature is fixed for few time, right? For up to this is the temperature. This is a time axis, right? That means from this time to this time gap, there is no change in temperature. So there is a temperature arrest, or I can say there is a discontinuity. Why there is a discontinuity? Because it should move like this without any steps. The curve should fall down without any steps, but here a step is there. So that is why there is a discontinuity in this plot. And you can say there is a temperature arrest. Can anybody tell me why temperature arrest is there? Why the temperature is not changing? You are cooling the sample, but there is no change in temperature. Why? What may be the reason? Obviously, there is a phase transformation is happening. Liquid iron is becoming solid iron. But why there is no change in temperature? Why the temperature is constant for some time?
State change.
Oh God, state change. That is all. I told you phase transformation. Solid liquid phase is converting into solid phase. But
Yes,
why
sir.
there is a constant temperature?
Sir,
So because
invariant reaction.
all the
See,
energy
the question is
used
when
in
you are cooling a sample,
it is a pure metal.
it is a pure metal. That's fine. But why the temperature is constant? That
So
is my question. The temperature
all
should
the
fall.
energy is used to convert the solid to liquid. So liquid to solid.
Okay, fine. Let me tell you. The thing is what some heat will come out during phase transformation. You are cooling the sample. You are cooling the sample means what? Some heat is coming out, right? The temperature should fall, but temperature is not getting fall. Why? Because some heat is coming out. That's why the temperature is constant. You understood? The heat is coming out due to this phase transformation. The heat is getting released from the material. From liquid iron, some heat is getting released, and that heat is coming balanced. That is getting balanced. From here to here, it is not getting balanced. You understand? So only heat is coming out. Only heat is coming out. Here, heat is coming out and it is getting balanced due by the cooling process. There is no change in temperature for some time. That is arrest. Okay, anyways. That means you understand at this arrest is happening at a temperature of 15, melting point of pure iron. 1538 or 1539. Again, you are cooling down the sample. The temperature is going down, 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 down. Then there again a temperature arrest is there. This temperature arrest is due to what? Due to temperature arrest is due to change in crystal structure. Right. It is happening at 1395 or 1396. See, temperature is 1396. Why the crystal structure is changing? Because initially from here to here, it is BCC. That is delta iron. People are calling it delta iron. Here, what is happening? Converting into another crystal structure, that is FCC. Again, this FCC iron is cooling down and down and down. And again, what happens at a temperature? There is a temperature arrest. This is happening at 910 degrees centigrade. What happens? The FCC iron becomes BCC. From here to here, complete BCC is there. But you can see some a small temperature arrest is there. Look. Why this is happening?
Magnetic property change.
There is a change in magnetic transition. There is a magnetic transition is happening. This entire structure is BCC, but there is a change in magnetic property. What kind of magnetic property will change?
From paramagnetic to ferromagnetic.
To ferromagnetic. Very good. Because high temperature means paramagnetic. Low temperature means it is ferromagnetic. So paramagnetic BCC iron will become ferromagnetic BCC. You understood now? You can conclude this topic, right? Cooling curve of a pure iron is showing many steps. What are the different steps? One step is due to phase transformation. Liquid iron is becoming solid iron. But in the solid state, we also can see many steps. These steps are due to change in the crystal structure, change in the phases. That is BCC to FCC and FCC to again BCC. But in the BCC also we can have a step that is due to magnetic transition. Paramagnetic BCC become ferromagnetic BCC. Crystal structure is same, BCC. And you can be able to see this is gamma iron, this is delta iron, this is gamma iron, alpha iron. But in between this called beta iron, some people call it beta iron. But beta iron, so what is the difference between beta iron and alpha iron? The similarity.
Same crystal structure but different magnetic property.
Very good. Alpha iron and beta iron have same crystal structure, that is BCC. But property is different, magnetic property is different. Alpha iron is completely ferromagnetic, beta iron is paramagnetic. So if I will give you a pure iron, which kind of crystal structure it will have? What is the nature, magnetic nature of that? Suppose I will hand over you a pure iron. Now, piece of pure iron. What is the magnetic property of that and what is the crystal structure of that?
BCC
BCC
ferromagnetic.
It is
ferromagnetic.
BCC crystal structure and it is ferromagnetic. It will be strongly attracted by magnet. This temperature is 770, but some in textbooks it is written it is 768. So you should not be confused. Okay, fine. So finally, what is the conclusion? That means pure iron is showing different crystal structures at different temperature. And what is the technical name of that? Technically, it is called which kind of transformation? Allotropic transformations. Or some people call polymorphism. Allotropism or polymorphism. What is that definition of allotropism or allotropic transformations?
Same composition but different structure.
Yes, same composition, different structure. So you can easily say a particular element or a particular compound is showing different crystal structures at different condition of temperature and at different condition of pressure. But here what we are taking pressure as a constant, 1 atmospheric pressure. We are only changing the temperature. So upon changing the temperature, we have a different crystal structure. So that is called allotropic transformations. Allotropic transformation means a particular element or a particular compound will show different crystal structure with change in temperature and will change with change in pressure also. Pressure is not, but pressure is constant here, 1 atmospheric pressure. But if you have changed the pressure, do you people remember what is the another crystal structure of iron if you change the pressure to a very high pressure?
Iron.
Look at this one. Temperature versus pressure for a pure iron. What is the crystal structure?
HCP.
HCP. What is this Greek alphabet?
Silent. Say Ita.
Epsilon. This is called epsilon iron or HCP. FCC, BCC, HCP, and this is again BCC. So you people are getting my point? If you change the pressure of the pure iron, very high pressure, it also takes a shape or take the crystalline form of HCP, hexagonally closed pack structure, hexagonal closed pack structure. Okay. So finally, what is the conclusion? The conclusion is, in the solid state, if we change the temperature only, we can have 2 crystal structures. One is BCC, one is FCC. But in the solid state, if we change the pressure also, we can get 3 crystal structures. Right? One is FCC and HCP. Is okay? But what about BCC? We can have a high temperature BCC. We can have a low temperature BCC. High temperature BCC is called delta. Low temperature BCC is called alpha. Right? Or we can call delta ferrite. Is called what? Only ferrite or alpha ferrite? Written over here, you can see. Pure iron, the temperature condition is the Greek letters, crystal structures. This is the figure. But here we are also considering the liquid. What is the structure of liquid? What is the structure of liquid? Liquid have a short range order or a long range order?
Short range.
Remember this. Have a short range order. Solids have a long range. If a material have a short range order, for here already.
Amorphous.
Amorphous. That is
Amorphous.
the one of the difference between crystalline material and amorphous material. Best example of amorphous material is a liquid, or you can call glass. Glass is the best example of amorphous material. In case of glass, we have a short range ordering arrangement of atoms. Right. So you people understood this one, I think. Already you have studied this one in physical metallurgy, fine. Or you can read it this one, polymorphism and allotropy. Polymorphism or allotropy means phenomenon where more than one crystalline form exists for a metallic element or compounds, depending upon the external condition of temperature and pressure. And what is the critical temperature? Already I have told you. A particular metallic element or compound changes to another crystal forms at a critical temperature, fine. And another interesting point is, due to change in the crystal structure, the properties also changes. Specific volume, thermal conductivity, electrical conductivity, magnetic properties like this. The properties get changed with change in crystal structure. And I would like to show you this. This is the heating cycle from room temperature to the molten state for pure iron. And this is from the molten state of pure iron to the room temperature. So what you are getting? Same thing, yes or no? The crystal structure is changing for a pure iron when you are doing heating. The crystal structure is changing when you are doing cooling. So now you can able to see some. Here C is written. Here R is written. Here C is written. Here R is written. I'll show you why C and R. Just look at this one. Upper critical and lower critical temperature. Do you people remember upper critical temperature is shown by what? A3, and lower critical temperature is shown by A1.
A1.
One is the lower critical temperature, is the upper critical temperature. A1 what sometimes represent AE1, sometimes represent AE3. So upper critical temperature, this is lower critical temperature. E represent what? Equilibrium transformation. There is an E, an equilibrium transformation. Equilibrium transformation temperature means if you are doing very slow rate of cooling, slow rate of heating. You have to represent by AE1 and AE. The moment you are heating only, you are heating the pure iron to the that condition you by AC, AC1. What is C? French word, chow phase. Phase is a means if I will give you a steel, if I will give you a pure iron, you are hitting the pure iron to a temperature. So what you need to write? Lower critical temperature, it is AC. Critical temperature, it is AC. We represent a French word called chow phase. Similarly, suppose I will give you a molten iron to cool it to the room temperature. In that condition, critical temperature you have to write R. AR3, AC1 and R represent what? The second French displacement, heal or cooling. You understood now? What is E? What is R? You know? People have understood, right?
Yes, sir.
Very good. And finally, I'll move to the new topic. Okay, moving into new topic, let me tell you. So, tell me one. So let me. If iron is shown in crystal structure and temperature, in the temperature on atmosphere, what is the significance of? Can you tell me the significance you are getting if iron is showing crystalline form? BCC, FCC. Let me see who can answer. Already I have taught you in IPM. I remember that.
We get different void size and all.
Get different voids. So what is the significance of that?
For substitutional solid solution or in
Substitutional solution. Yes, yes. Saying something.
interstitial solid solutions.
Do you people agree?
Doping and all.
Do you people agree with Sibasis? If we
Interstitial, sir.
interstitial, obvious
Into void.
substitution. Void size is
Yes, sir.
small. Interstitial voids, na? Remember how interstitial form between the parent atoms. It's very tiny space parent atoms. Tag the AB or ABC. It's a very small void size. How you can add a substitutional alloying element? Not accommodate a substitution. Accommodate a interstitial alloying element like one your hydrogen, nitrogen. Those atoms can be accommodated over there. Fine. But in terms of iron, advantage. This is
So the saturation limit changes.
saturation limit means what?
Limit to the extent to which we can add carbon.
Changes. Can you
The
justify that?
open structure and the closed structure.
Significance of open. Means
For open structure, the diffusibility of carbon will be more.
diffusibility or diffusivity?
Diffusivity. For closed structure like FCC, the solubility will be more.
Fine. I didn't understand exactly what you mean to say, but let me. I told is a very interesting. Different temperature, it is different. And it is interesting. The advantage. You can see discuss in terms of probability of what? Main interstitial atom?
Carbon.
Carbon. Okay. So, thing I will write over here. So that means C, BCC iron. BCC iron, what is the nature of BCC? Everybody agree? Post extraction. See, FCC is a closed pack structure. Closed pack structure means packing is more or packing efficiency is more. fraction is more. Is a open structure means packing fraction is less or packing efficiency is less. Remember what is the packing efficiency of FCC?
74.
Very good, 74%. You remember that. We have also calculated that in IPM. For this one, how much? Packing efficiency?
68.
68%. Okay. But if you look into the solubility, okay, so now another one is, okay, let me explain here. See, FCC iron is a closed pack structure. It is having a packing efficiency of this much. The void is less, right? So void is more here. Void is more here, void is less here, obviously. But do you remember that I told you basically in which voids the interstitial atom goes into the iron? Because there are two types of voids, octahedral and tetrahedral. Basically, it goes into the octahedral void. Very good. Can anybody remember what is the position of octahedral void in FCC?
So one at body centered and 12 at edge center.
Very
Edges.
good. You remember, Sivasis remember that. One is the edge center of the FCC and the one is the body centered. Very good. What about BCC?
Faces and edges.
Edges, very good. Edges, very good. Edges, and another one is the face.
Faces.
Face, very good. Sivasis remembered. So the point is what? In FCC, I can write here octahedral. Okay, I'm writing octahedral void is bigger, right, in size. But here tetrahedral void is bigger, or you can write octahedral void is smaller than octahedral void of FCC. You people understood now? Let's look at this one. I told you in case of BCC iron atom carbon atom should goes to the tetrahedral void. It is bigger, but it never goes because it will generate more strain in the BCC, right? So what will happen? It will obviously go to the octahedral void. You understood now? Right? It should go to the octahedral void now. But what is happening? Octahedral void size is small as compared to the octahedral void of FCC. So that means size is the main factor for the solubility. You understood? Now, size is the main factor now. So size of the octahedral void is bigger in case of what? FCC iron. So what will happen? Solubility is more. And here solubility is less. You understood my point now? Because the solubility of the iron is depending upon the size of the void of octahedral size. If the octahedral void size is bigger, solubility is more. If the octahedral void size is small, solubility is less. So that's why FCC iron have a more solubility for carbon atoms. What is the maximum solubility in FCC iron, or what is the solubility limit basically from iron carbon diagram? It is how much?
2.11.
2.1. Very good. 2.1. For BCC, how much?
0.77.
0.77. What you are saying? 0.1. It becomes 0.77. It is not a solid solution. Do you think it is a solid solution? Solid solution means everything will be getting soluble in the matrix. You people have forgotten. That is how much?
0.025.
0.025. Very good. But it is weight percentage always, huh? Weight percentage. Weight percent, huh? This is weight percent. You people now, what is the advantage you are getting now? Different crystal structure, but different solubility. due to size of the void only. This is. But what about diffusivity? Do you remember? In which case diffusivity will be more?
BCC more
BCC diffusivity will be more. Yes. More. Why? Question is why?
open structure.
Open structure. Very good. But here diffusivity will be low due to closed pack structure. Right. So that is why one of the reason we use this. Listen it carefully. Due to this reason only. Listen it carefully. Do you people remember which kind of failure basically takes at high temperature? What is the name of the failure? I think Dinesh Shah might have told you. I have told you somewhat. I remember. At high temperature application, suppose the temperature is 660. Creep. Very good. Creep. In the creep, what is the main role? Diffusion is happening, right? Due to diffusion, you have to remember creep is a very dangerous failure because basically creep happens below the yield strength of a material. Below the yield strength, there will be a permanent deformation and it will fail. Very interesting. And creep basically occurs at a very high temperature. Why? At high temperature, what happens to the material? What kind of defects generates at a high temperature? Which kind of equilibrium defects generates at high temperature? Vacancies. Vacancies, no? Why you people are you go through the IPM notes at least, huh? At high temperature, vacancy generation occurs. A lot of vacancy generates. And vacancy once generate, vacancy means there is an empty space, atom is missing over there. So diffusion will be more better. And temperature is high also. So diffusion, due to diffusion mechanism, the sometimes creep failure will occur due to presence of more vacancies. So vacancy also helps in the dislocation motion. That is another interesting point. Dislocation motion will be more easy in case more vacancy will be there. That is very interesting fact. Anyways, so what I mean to say is that is one of the main reason. Due to this reason, we can use superalloys. So superalloys are made up of iron basically. Iron-based alloys, nickel-based alloys. There are superalloys. So you understood now? That means why iron? Can anybody tell me why iron can be used as a superalloy? Superalloy means those alloys which can withstand very high temperature. It will not fail at a high temperature due to creep. Creep will be not easy in case of iron-based alloys. Why? Just look at this one.
At high temperature, diffusivity is low in iron.
Very good. Why diffusivity low at high temperature? Due to
FCC structure.
Due to FCC structure. Very good. That is the answer. Since at room temperature, iron is BCC. But if you have an application of a iron material at high temperature, this BCC iron become FCC iron. Once it become FCC iron, it is a closed pack structure. Once it is a closed pack structure, diffusion becomes slower. So creep will not occur easily. There is a resistance to the creep failure. Now I think you people understood. These are the two things. Okay, fine. Next. Okay, I will stop here. I will start the class from the next lecture. I will discuss this stress strain curve and properties. We'll discuss properties and we'll discuss defects in the crystalline material. If you want, you can go through the IPM notes about the defects present in a crystalline material. Okay, you can leave